Hey guys, this is Dr. Cortez, and I just wanted to finish up where I left off on in class on Tuesday or Thursday. So this is going to be your class notes in your video for Tuesday's class, since I will be at ACS. Note that there will be several videos within this for this Tuesday's class, and so I will upload all of them to D2L as we go through. So where we left off in Thursday's class is talking about polysaccharides. So remember that these are going to be many units of sugar, so they can be all of the same types of sugars, such as our polysaccharides, or they could be made up of different types of sugars, being your heteropolysaccharides. Okay, so before we move on, I wanted to test your understanding to answer this question. So go ahead and pause your video and try to answer this question. All right, so to be able to identify which disaccharide would be a reducing sugar, remember, being able to be a reducing sugar, we have to look for the capability of having that hydrogen that can be oxidized on our anomeric carbon. So if we look at these two disaccharides, here is the anomeric carbon that's free, okay? And so if we look at this sugar, okay, we have an alcohol group here and a free hydrogen. So in this case, this would naturally, in a straight chain form, would indicate that we are dealing with an aldose type of sugar, which can be oxidized. And so therefore, it would be referred to as a reducing sugar. If we look at our sucrose molecule over here, also over here on this disaccharide, when we see that in the straight chain form, it would form a aldose, we know that this structure here is a hemiketal or hemiacetal. Over here, we're dealing with our anomeric carbon over here, and we see that this would be our hemiketal, okay, or our acetal group, okay. And so here we wouldn't be able to oxidize this any further because we don't have that alcohol group available, okay, which would have been right here. All right, so hopefully you could be able to identify a reducing sugar by looking at your anomeric carbon and determining, do I have opportunity for our hydrogen that could be oxidized or not, and looking for our hemiacetal structure, so right here, or if we're looking at an acetal. All right, so moving on. We already talked about amylose and amylopectin. These make up our starches. However, I wanted to make sure that we talked about them in relation to cellulose and glycogen. So remember that amylose is our straight chain polymer, and it has our alpha 1,4 linkages. Remember, it has the 1 because it's on the first anomeric carbon, okay? And then 4 because if we count our carbons in our sugar, we have 1, 2, 3, 4. And it's alpha because it's down. All right, so our amylose forms a cyclical structure, a helix form. And our amylopectin, however, has a bunch of branches coming off of it. And so this is because it not only has the straight chain alpha 1,4 glycosidic bond, but it also has the alpha 1,6 glycosidic bond that allows it to branch. Okay? both of these polymers make up our starch molecules, and they're both made up of our monomer unit of glucose. Let's see, what else? This is how plants primarily store their energy for short-term use. And amylopectin degrades faster because of all of these branch straight chain structures, as opposed to amylose that would only have one reducing end. Amylopectin would have multiple reducing ends on each end of our amylopectin molecule. All right, so if we look at glycogen, this is how animals primarily store their glucose, and this is used as our short-term energy within, well, it's used for long-term energy storage. So, or short-term energy storage. And if we want to store energy for the long time, we convert our carbohydrates into lipids, because as we talked earlier, our lipids are highly reduced and therefore can provide lots of energy by being oxidized a lot. Okay, and so as you can see, glycogen is branched similarly to amylopectin, so it includes both alpha-1,4 and alpha-1,6 bonds. So here's your alpha-1,6 and here's your alpha-1,4, and it's also a glucose monomer that makes up our glycogen. All right, cellulose, on the other hand, still is made up of glucose monomer units, but as we can see from the structure, it has a beta-1,4 configuration. Okay, and so if you remember, our alpha amylase that breaks down our polymer is specific for the alpha anomer, and so therefore our bodies can't break down cellulose. And this is what plants use as their structural material. Okay. Our glycogen and our starch are what plants use to store energy. Plants and animals use to store energy. Cellulose would be what plants use for structure. All right, so how do we utilize cellulose, right? We can't break it down. Well, this is what we refer to as fiber. And so we should all be familiar with what happens to fiber in our body. It helps things move through us quickly. And it's because we can't break it down. We don't have the enzyme to break down these beta-1,4 linkages due to the stereochemistry specificity of the active site of our alpha amylase. All right, so how does cellulose provide structure to our plants? Well, it's all about hydrogen bonding. The same thing we keep going back to. So if we look at the structure of cellulose, we have a ton of oxygens and hydrogens on our glucose molecules that can hydrogen bond and form this big complex structure of cellulose. And so that rigidness of the hydrogen bond network provides the structure for our cells. So some species do have enzymes that can hydrolyze the polymer, the beta-1,4 linkages. However, we do not. Okay, that's important for you to know. All right. The final polymer that we are going to talk about is chitin. And this is what provides insects with their exoskeleton. Chitin has a different monomer unit. It uses N-acetyl D-glucosamine. Okay. And you'll see here is your N-acetyl group, and your basic sugar molecule is going to be your glucosamine. This is actually what doctors have started moving towards is using chitin as surgical thread because it's biodegradable and it's flexible and super, super strong. The other aspect of this that I want to make sure that you're familiar with is glucosamine. So these are the tablets that you typically take when you're older for like knee and joint health. And so all of this helps provide, and your carbohydrates help to provide collagen support, which is kind of our shock absorbers for our body and our joints. Okay, so I'll give you a second. Go ahead and pause the video right now to go ahead and answer this question. All right, so the starches amylose, amylopectin, and glycogen are all homopolysaccharides of alpha-D-glucose. Which of the following statements are true about the structure and function of the starches? Okay, so amylopectin is the most highly branched of the structures. This is false. Glycogen is actually the most highly branched of the structures, and that is one of the reasons why we get so much short-term energy from that structure. Amylose is unbranched and can adopt a helical structure. This is true. Remember, amylose only has the alpha-1,4 linkages, and it coils up in the helical structure. Their function is primarily as structural components of cell walls. This is false. Each molecule of starch has only one reducing end. So this is false because your amylose has one reducing end. Your amylopectin, however, has many. And that's why amylopectin is so useful in breaking down getting energy from first. Glycogen contains both alpha-1,6 and alpha-1,4 glycosidic bonds. This is true because you have the branching and you have from the alpha-1,6 and you have the straight chain form from the alpha-1,4. All right, so the final slide for the finishing up chapter 10 on carbohydrates. Go ahead and take a second, pause the video, and answer this question. Okay, so remember this is our Fisher projection. So when the ring has been flattened out, we refer to it as the Fisher projection, and the Haworth projection is our ring structure. So how we determine this is we have to flip it over onto its side, okay? So how we go about doing that is we know that the carbonyl is going to be the anomeric carbon. So here, okay, so the pink carbon on each of these. And if we turn it on its side, that's going to be the pink carbon. So if we count the oxygens as to whether or not they're up or down from there, that will tell us the given Haworth projection. So here, carbon 2, the OH should be up, which knocks out A and B and D. Okay, so that automatically tells us that C is the correct answer. Carbon 3 is the OH is up. Okay, and then remember, if we keep it on its side, carbon 4, the OH is down, and carbon 5, remember this oxygen is the oxygen in our ring, okay? That has nucleophilically attacked this carbonyl to create our ring structure. All right, so hopefully that gives you a review of carbohydrates, and if you have questions about how to draw a Haworth projection, I'll post additional videos to give you some practice. Look forward to the videos on digestion and metabolism basics, which are all required for Tuesday's lecture.